Hello friends, welcome to class 12 lecture of the course FEA of Aerostructures. So this is going to be the very last lecture of this course. Uh, in this lecture I am going to uh, take you through the FEA overview, and also I am going to show you some of the case studies which I had done in the past, just for you to understand how we can use various different things of whatever we studied related to the theory of FEA while implementing into the practical real life scenarios. So quickly jumping into the slides, first I will take you through the best practices, and then also I will show you some of the case studies. Towards the end of the lecture, I will present you possible interview scenarios for an FE analyst or stress engineer roles, and also I will be showing you the challenge or the final project which you have to undertake, and I will explain you what you need to do in terms of the tasks. So starting with the best practices, so far in this lecture we have been discussing uh, many things about meshing, about loads, boundary conditions, material properties, etc. So one of the first and foremost, and I would say the important thing, is starting with the meshing. So during the class 3 lecture, I have been taking you through various different options and features for meshing within Patron and Astron, and I have also mentioned to you the best practices in meshing during that lecture. So just to revise you and brush up the best practices within meshing, if you see, the first and foremost thing that comes for a stress engineer as a challenge is idealizing the geometry correctly and building up a mathematical model. So one has to accurately understand the physics behind the real model, how it functions, and what are all the constraints and what are all the parameters they need to consider for their analysis before starting to build up the mesh or the mathematical model. So one of the things is like to discretize the domain into finer elements, and then choosing the right element that comes next, and choosing what order of elements for what kind of analysis that comes next, and then choosing the loads, boundary conditions, materials, and so forth. So one of the measures of accuracy in finite element method is nothing but it's based on the error it gives when we compare the errors which is given as output from the solver or the FE tool against the hand calculations or the closed loop solution or the closed form solution. So in that way you can point out what is the error percentage it can give. Suppose you have a large model in a typical strength of materials approach or the mechanics of materials approach, one can possibly idealize the same model to a beam, and do a very quick and very rough calculation just to see how the deflection and what range the value of deflection would be. And similarly, if he runs the FE tool and if he gets the value in that range, he can have some satisfaction at the back of his mind, saying that at least he could able to correlate with his hand calculation and to have the justification saying that the analysis whatever he has done is correct. So within the finite element terminology, we say it is H H convergence or P convergence or H type or P type. H means you are increasing the number of elements, and P means you are increasing the polynomial order. Polynomial order in the sense you are going for higher order elements. Suppose that if you take a triangular element, a normal tria element will have 3 corner nodes. The higher order element will have mid-side nodes, so etc. So especially if you look at the area of stress interest, where suppose you are dealing with a very big assembly, it's not necessary that you have the entire assembly to be your area of interest. There will be some particular area of interest within that assembly that you are going to watch for the stress levels, you are going to watch for the deflection. Suppose if I am handling a door assembly of a typical Airbus aircraft, my area of interest would be the maximum deflection at the center of the door, and when it comes to the end towards the boundary, suppose imagine this is a square door, my area of interest would be the center portion where the maximum deflection would be, and in the boundary where it is attached to the aircraft surround structure, the door surround structure. So there will be different areas of interest within the model. So in those areas the mesh should be little bit finer. So it depends on the FE analyst how he is idealizing those areas of attachments and those areas of where the maximum stress is expected or where the maximum deflection is expected. All should be backed up by a necessary hand calculation or a very rough calculation to have an idea, to have a clear understanding where you can expect these parameters. So let's jump into the case study. Case study 1. This is one of the horizontal stabilizer which I did long back. I can't mention the name of the client or name of the company or name of the product, but this horizontal stabilizer, if you look at this, attaches to a head stab very big lug that attaches to the one of the center ribs on the stabilizer to the fuselage area. So my area of interest is the attachment location where I have put the finer mesh in order for me to capture the stress distribution more accurately. Whereas if you look at the lug, little bit the mesh is coarser, and even the panel, when I move from the attachment area, I gradually increase the size and little bit coarser mesh. Why? What is the reason I have put a finer mesh? Because I know that the stress distribution, the forces will be reacting at the attachment areas when the applied force is acting on the panel. The attachment is only through the lug. So the my kind of interest, as I mentioned now few seconds back, is the stress distribution within the panel in the attachment area. So that is the reason I have meshed using finer elements, increase the number of elements in the attachment area. Similarly, if you look at the bottom figure over here, there are two L brackets presented, and one has to know how to model this attachment brackets in detail and where. So it's the duty of the FE analyst to understand clearly. For example, if I model the 2D bracket, if I model the bracket as with the 2D elements, that means my interest is not the bracket, because I don't want to know the force distribution or the stress distribution within the bracket, my area of interest would be the panel joint. And if I model it with 3D elements, that means I am also qualifying, I am also certifying the bracket, I am also going to look for the stress distribution within the bracket. At the same time, I am also going to look for the panel or the structure that is being attached to this bracket or to which the bracket is attached to. If you look at the typical aircraft, the overall global finite element model of the aircraft will be very coarse, because those coarse models will be used just for pulling the loads, pulling out the loads. They'll be used only for extraction of loads from the various different components or the interfaces within the model. If you just go into the just wing section alone, it will be much more finer mesh than the global mesh. And if you further go into the just an attachment area within the wing, then the fasteners, bolts, brackets, and these kind of brackets will be modeled using 3D elements. Why they model these brackets and fasteners in 3D elements is to capture accurately the load distribution at the interface locations. When I say interface, interface means it's say attachment or connection locations, that is connecting something to something, something with something. So in this case, it is connecting a bracket to the composite skin panel, or it may be a composite or metallic. So, but the area of interest will be that should be modeled in detail. That's what I want to say. So the basic difference is, when the bracket is modeled using 2D elements, my area of interest is not this bracket, my area of interest is something else. So finite element analysis should always use the, you use the meshing as a tool that would that which with which you should be able to generate mesh in detail only for the areas of interest, and for the remaining areas a simpler idealization would do. Now, going back to the best practice, as I mentioned, in this slide, this is a simply a plate with a hole problem. My area of interest is the stress distribution surrounding the hole. I want to know how the stress distribution varies with the hole. So, since my area of interest is this one, I have meshed it with the fine mesh. Suppose my area of interest is not this one, but my area of interest is just the loads going through the attachments and everything. So I need not waste my computation time in meshing the model with a very fine elements, because more the fine elements, the more the computation time and more the processing time and more the memory it takes and more the time it takes to generate the output to compute the forces across these elements. So I can idealize this one as a simple with a very coarse mesh and give importance to the attachments. So as an engineer, as a FE engineer, you should clearly understand what is your area of interest before analyzing any geometry or before starting up with any analysis. So now moving to the second case study, this is a typical plate with a hole problem, but in this case we have I had meshed it with quadrilateral elements. This is a 2D plate. So I took this project just to understand the effect of pin shear. The client asked me to execute this project for various different E by D and W by D ratios of the plate with the whole problem and with the pin loading. Imagine this is a panel on the aircraft wing panel or aircraft fuselage panel, and this hole is the bolt hole or rivet hole, and there is a shear loading coming through the pin, and I want to study what is the effect of this shear loading that is being transferred from the pin to the plate. So I model the loading with three different types of loading. One is directly applying the load as a point load, and another one is creating a pressure load in the circumference of the hole using cosine loading, cosine formulation, and another thing is like using the gap elements. So and then before starting the study, I did a convergence study. I want to see how the stress varies, and I arrived at the optimum element size, that it doesn't vary much. And you can see this typical example shown here for 2 by 2 inch plate with a 1 inch hole diameter, and you can see the stress peak stress distribution around the hole. When I calculate the kt is the stress concentration factor for a circular hole, which is 3 times the sigma. So when I calculate, it is exactly matching with the stress concentration, Peterson stress concentration factor. There is a book that gives the theoretical value. You can see the stress contour plots, one for the case which is with the cosine distribution of the load around the hole, another one is the gap elements. You can see the variation in the picture. So the one with the cosine loading gives the peak stress of 12.3 ksi. Ksi is 10 to the power 3 psi, pounds per square inch, and the gap elements gives 12.8 ksi. There is only 0.5 difference, but they are really close. So since I use the gap elements, it's a nonlinear run, nonlinear gap elements. So now moving to the third case study, we have I did work with the elevators, which is the typical composite panels within the aircraft. So composite sandwich panels. So over here I have shown you the mesh that I've created, and these are all the vectors, element normal vectors, just to make sure that the elements are uniform across the panel. And these are all the different material properties, different layers of the composite elements. So if you look at this slide, you will understand that the mesh is not that fine. It's a bit of coarse mesh. It's a Since it is a 2D mesh, I went with fully quad elements. I tried to minimize the usage of tria wherever possible. I tried to use with quad elements, and then the the end caps or the flanges of the spars, ribs, those are all modeled using the p bar elements, and the ribs are also meshed using 2D elements, and then the rib flanges are modeled using the p rod elements or c rod elements, 1D elements. And I haven't modeled anything as 3D. The mesh was generated from the geometrical midplane. The midplane was extracted from the geometry, and then I started generating the mesh, building up the finite element model. And all the connections between the ribs and the spars and the skin is done using CLAS elements, which is the spring elements. Based on the rivet or fastener stiffness, I calculated the fastener stiffness using Hutt's formula, and then mentioned those into the properties, fed those values into the properties. After completing the mesh, the model was run. I did a free modal analysis for the first 10 modes just to check the model is proper and everything is connected. So it looks that I got the output for the first 10 modes is 0. That indicates that the model is very well connected. There was no error. And finally, I did run the model for some pressure loads, extracting the natural frequency or eigenvectors and eigenvalues of the elevator panels. So this is the force resultant and the applied load resultant. This is the constraint force and the applied load. So both from the F06 file, just to make sure that everything ties up really well. So the applied load should be equal to the reaction force generated. So moving to the one another case study is the this is for this is I ran this global model or the loads model just to understand the deflection of the fuselage and wing, and to generate the test condition, that is the aircraft being tested in the test lab, in in order to generate those test conditions within the finite element tool using finite elements. So the aircraft was a VIP jet, and then I did run for both positive wing bending, up bending and down bending, negative wing bending case, and there were lot of wing stations across which I have to apply the pressure loading. And this is a global model, and model was built by someone, and it had few connectivity problems. So I just corrected that, and then I I created a MPC elements, which is RBE2 elements, sorry, RBE3 elements, for creating the pressure loading, because I don't want to add any stiffness to the structure. So that's the reason I went to RBE3 elements. And it's also an interpolation element. So when we apply the load at the dependent node, it would based on the lengths, uh, it would distribute the loading to the independent nodes. So along the wing, there are some various wing station numbers with respect to the ribs positioning and with respect to the spars. So it was a distributed load, and then I have to, based on the small chunks of areas, I have to convert to the equivalent pressure load, and I have to apply. And then what I achieved is the positive bending and negative bending. And when I correlate the result against the tested loads, they tested this aircraft in the test laboratory for the same bending case, and the results were really close. And the final case study is the aircraft interior galley analysis. And if you look at this galley structure, it is mainly carbon composite or glass fiber composite structure. And you know that the galley is used for storing foods, and the flight cabin crew used to heat, and then they used to distribute the food. And there will be some trolleys, and there will be some food shelves and food boxes that they will use to store the food, and then During the flight, they distribute to the passengers. So the entire structure is made of glass fiber composite. With they have this kind of galley monuments. They have attachments to the lower to the aircraft flooring panels, and at the same time they have top attachments which is attaching to the aircraft roof, aircraft ceiling. So I built up the finite element model, which is again 2D model, which is mainly quad elements have been used wherever applicable and wherever possible. And then all the attachments I modeled it using MPC elements. The lower attachments are modeled using RBE2, and the top attachments, you see the strut which is attaching to the aircraft roof, that is modeled using a bar element, and then the topmost strut is using rod element, and then the there is a lug. There are two lugs, which one lug is coming from the aircraft roofing, and other lug is coming from the strut, end of the strut, that is attaching to the aircraft bracket, aircraft lug. So that is the pin is idealized using CLOS element, which is the spring element. I calculated the spring stiffness in all the three directions, and then I input those values to the CLOS element. And this is the location and coordinate of all those attachments and fittings. And mainly these galley monuments are run for inertial load cases on the gravitational load cases, because they have the flight cases, different inertia cases, like forward direction 6g, sorry 9g, and then flight aft inertia, rearward inertia is 3g, and those kind of inertia cases. So and these galley monuments will be analyzed for those kind of inertia cases, and also for the rapid decompression cases. Rapid decompression is the whenever there is a hole or puncture in the structure of the aircraft during the flight, since the um, pressure within the cabin is more than the outside pressure, and the pressure tries to run from the aircraft to the outside. It tries to move from the high pressure region to the low pressure region. That is called cabin rapid decompression. So if you look at these pressure loads, these are based on the cabin rapid decompression loads. And in terms of the mass that is being applied, so I modeled the spider using RBE3, and I simply applied converted the mass times 9.81 gives the force. So applied those forces on the structure, and each and every panel will be connected to the neighboring panel using they connected using the fasteners, using they have a special type of eye lock rivets and those kind of rivets that is used for connecting the panel, and they have glued connections called tongue and slots, which is like mortise and tenon joints they call. It is basically used for it's something like gluing together. So those glue is idealized as RBU2 elements. So I have glued all the 6 degrees of freedom of one panel to the another. That means they stay intact. And then coming to the upper attachments and the strut is, as I mentioned earlier, this one model. There is another model where I model the upper attachment using 2D elements, and then the final strut is using C rod element. Whereas in one other model I modeled the entire structure as bar elements, and then the final rod as using the C rod element. So running for the inertial load cases, can understand that there is combination of the inertial cases as well, and you can see the deflection plot, and then also the interface forces, the forces at the attachment points, those MPC forces have been extracted, and you can see the computation of the result factors. So if you look at the aircraft lower attachments, so since the whenever I ran the model, the aircraft galley as a whole, my area of interest was the deflection and stresses within the galley structure on the composite panel, and not the attachment area. So I modeled it using MPC, and whenever I modeled it separately to understand what is the load distribution within the lower attachment alone, I modeled it using TET element, using TET measure, and then the lower attachment. This is a lower attachment fitting that sits over here in this area. This is a typical lower attachment. It is a heavy aluminum machined fitting. So I was asked to study the load distribution within the fitting. So since my area of interest is only the fitting, I generated the mesh using the TET measure, and then I for the bolt connections, there are like 7 fasteners that is attaching this lug to the aircraft galley panel structure. So the this bolt locations have been modeled using spider elements, which is RBE2, and finally this is the lug hole or the pinhole that attaches pin that is that attaches this lower fitting of the galley to the aircraft floor structure. So that is again modeled using RBE2, and then I extracted the loads, whatever loads that have been extracted at the attachments from the global model will be applied to the local model, and then and this will be constrained, or at these points the master node will be constrained all the 6 degrees of freedom, and then I ran the model, and you can see the stress distribution, which is the principal stress distribution within the fitting. So there are some, I would coin it as golden rules of the finite element modeling. So one is simplifying the model, one is eliminate the complexity, and idealizing, doing a very proper and doing a very, if not accurate, at least an very close enough idealization just to bring down the complexity of the model, and then select the proper element types and the number of elements and the mesh, and also look for the information what you are after. You should understand the model, understand the function of the geometry that is being given. So understand the load paths, you should understand the load paths, how the loads will be distributed within the model. In that way you can come up with a very nice and simplest model, but at the same time very mathematically very powerful, that would provide you the results that would correlates with your hand calculations or any other justification. So another thing is the, I would say, quality. So some of these points have been already covered in the first point. So both prior to the analysis and after the analysis, so after the results generated, so you should be able to justify why you have selected the mesh and why you have selected this element. For example, for a panel, simple 2D panel kind of geometry, you can't use the it's not you can't use you can use the 3D elements, but unnecessarily you're making the model complex, and then you don't have the proper justification once the analysis had been done. And then understanding the assumptions, as I mentioned, so one has to understand the assumptions in terms of especially the attachment areas and the constraint areas, and then finally verifying the results. The results should verify whatever number that the FE tools throws back. One should be able to verify and make sure that it makes some sense, the values make some meaning, that it is of the proper order, or it is what something around the range, ballpark range, I'm expecting, or it is what it is expected. Suppose the finite element tools give you a stress of 200 times 10 power 8, that means you should be really spurious why such a very high value of stresses come into picture. So what is the mistake I have done? So you have to go back and dig into the mesh, dig into your assumptions of the boundary conditions, just to properly whether you have properly represented the actual phenomena. And then if you don't verify the results, and if you on based on the FE results, if you make further design decisions and release the product into manufacturing, so it's going to be a faulty product. So it is always there is a risk that, because most of the companies, they do the carry out the testing and they want the FE engineers to correlate it against the testing, or sometimes if they don't have the time for testing, they go for, based on the finite element analysis, they do a very quick hand calculations, kind of rough calculations, just to make sure that everything works proper, and based on that they go for the final product drawing release and certification. So if the finite element is analysis, if it's not proper, if there is a mistake and if the analyst couldn't point the mistake, or whatever mistake he has done, so it's definitely going to affect the product once the manufacturing of the product is been done. And once the product manufacturing done, and then when they test the component, it's going to fail. So in that way it's going to be a way of misleading. The analysis will be totally misleading if the important assumptions and the results, if it is not be able to verify, or if it's not be verified. So one has to be really careful in making the decision, or in making what kind of assumptions you use, and what kind of, right from the meshing, as I explained a couple of times before now, what kind of loads you are using, what kind of analysis you are carrying out, and everything should fall in the place just to have the right product to be certified, to avoid any accidents. Now, discussing about the possible interview scenarios for an FE engineer, most companies would ask you to take you through the experience, whatever you are. Suppose if you are a graduate engineer, fresh engineer, they would ask you, what they would check you, what is the understanding of you on the finite element analysis. So they could throw the questions from the basic strength of materials, such as what is the difference between von Mises stress and principal stress. It looks simple, but it it will check your understanding. And mostly in the most case they would ask you to, it's quite few times they would ask you to derive an equation or write an equation for the rod element or the governing differential equation for a beam element and those kind of stuff. But in the most cases they would check your understanding just to know what kind of loads would be carried by what kind of elements, and also what is the, they would give you a plate with a hole and they would ask you to mark where is the maximum stresses developed and why and what kind of idealization you would do in such a scenario. And suppose you have a big, during the case study we saw that a galley structure, they would show you some structure something similar to this, and they would ask you, suppose if the attachment fails, then what would be your necessary course of action, just to understand. Suppose if you ask me what would be my course of action, I would first come back to the model. I would check why the attachment is having the high loads. Is it due to the assumption if all my things are correct, that means the galley is experiencing a very high load, or is my load paths correct, or the connection between the panels correct? If it is a high load, then what is the way you can pass, you need to come up with a local stiffening where the, on the panels which are experiencing a very high stress, and then mitigating the problem using hand calculation. You can justify the metallic fittings using hand calculations and the remaining rest of the structure using finite element analysis, or it might be a combination of both hand calculations and finite element. So those kind of questions would be typically just to make you think what will be your course of action when this is happening. And this is happening, and imagine they could show you a picture something like this, a panel with a bracket or bracket, and they could ask you to mark the free body loads. What is the free body loads on the bracket, and why you need to idealize using 2D, and why you need to idealize as 3D, and what is the degrees of freedom between 2D elements and 3D elements, and those kind of questions. So they are mainly after checking your understanding of the concept rather than you giving importance only in deriving the equation. But at the same time you should be thorough with the fundamentals. When they ask you to mark a simply supported beam with a UDL or simply supported beam with a couple, you should be able to mark the shear force and bending moment diagrams. And also you should be, when they give you a load, you should be able to mark what is the tension clip. Suppose you have, suppose imagine a bracket like this. There was question in my interview when I attended. In some of the companies they give a bracket like this and with two fasteners on either side, and you apply a load, they would expect what kind of loads the fasteners would take, those kind of free body diagrams for the shear clips, tension clips, and these kind of brackets you should be able to mark it. And you have a thorough understanding of the Nastran chords. Sometimes they might ask what is what Nastran chords, and what kind of elements take what kind of loading, and sometimes they will ask what is the difference between RBE2 and RBE3, and what is your understanding on that, and where you will be using RBE2 and where you will not be using RBE3, and where you will be using RBE2 instead. So these are all the typical questions that you could expect in an FE analysis or the stress engineer role. Mostly I would list down as the beam. First of all, one should be really thorough with the shear force and bending moment diagrams and understand how the load varies within the beams, and importance of the different various different connections, whether it is clamped, whether it is hinged, and the application of the loads, whether it is a couple or whether it is a uniformly distributed load. And number two is the understanding of the finite elements itself, like what kind of loads that an element will carry and how many degrees of freedom will have each element, and how you will idealize the complex geometry, that is which this many different attachments, how you will be idealizing in the finite element, and what happens if the your attachment fails, and what is the difference between the stresses principal von Mises and what is the stress tensor and those kind of questions. And what is the difference, suppose you are going for an typical aerospace FE engineer role, because most of the aerospace applications are composite and metal, they could ask the questions from the composites as well. What is your understanding on the composites? So though the composites is not covered in this course, I'm just giving you a typical scenario of how they will ask you about the composites, what is the anisotropic properties, and how you can idealize the composite within the finite element, and what is the pcom card in the nastron for composites, what are all the parameters you need to specify, and what is the output you will look at, and what is the stress you will take for core. For core we take core shear stress, for skin panel we take the maximum in plane stresses. So those kind of questions. So with this I would thank you very much for listening the lecture, and I wish you very all the best. I wish you very best for your future in your future endeavors. So I will record a quick video for the instructions on the final project. Thank you very much.